A2 will look at something called Gambler's Fallacy. So the introduction to that is this game called roulette, where a ball is spun around on a roulette wheel, and it lands either in a red or a black slot, and there's also a small chance it will land in green, but we ignore that for the simulation. The chance of a ball landing in the red slot is the same as it landing in the black slot. Some gamblers use the following strategy for winning at roulette. They watch a wheel, and if it gets a certain number of reds in a row, they bet on black, since they think that red is due, or black is due. And similarly, if they see the ball landing on black, a bunch of times they'll bet on red because black has happened so many times before. So here's an historical example. In 1913 at the casino in Monte Carlo, black came up 26 times in a row. By about the 15th time, people started betting on red because they thought it was now red's turn. And as a result, the casino made an enormous sum of money. So in class, we watched this, just kind of this intro, this man betting his life savings on red or black. So I'll show you part of it. The quality's not really good, so I'm not going to zoom in. All right, so I'll just give you kind of the rundown. We'll watch it in class, but this man had $136,000. He played it on a game of roulette.
Their entire life savings, but we know that this is a culmination.
So he ends up betting it on red, and then we just watch the wheel go around here. So it lands on red. By no means should you go and bet your money on this, but you can see that, there's a 50-50 chance of this happening. So there's kind of our example there. And so what we are going to explore in class today is something called Gambler's Fallacy, which is if you have a bunch of colors coming up, does it pay off to bet on the other color since like a bunch of one color popped up and the other color is due? So we're going to do an experiment where we flip a coin, and we're going to flip it 25 times and record our results right here. So here's an example. Maybe we get heads, tails, heads, tails, 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 heads, tails, heads, 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 tails, 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 heads, tails. Okay, so I'm just making it up. Okay, so let's say you flip, and here's the results that you got. Now we're going to look for something called triplets. Triplets are when three things in a row happen. So my first triplet is these three tails in a row. And then we're going to take a look at what happens after. So we have three tails, and we look at what happens after, and that is different, right? We get a heads instead of a tail, so I'm going to mark that down for different. Now I'm going to look for the next three in a row. This time it's three heads in a row. And I look at what's after, and that's the same as what happened before. So there's a same. There's another same. If we look at our next three heads and another head, so another same, and then we have another three heads in a row, and now it's different. So again, you're looking for triplets, three in a row, and you look at what happens afterwards, and it's either going to be same or different than what happened before. I think that was all my triplets. And then we're going to take a look at our data and our class data. So what happens in class is as we do more of this experimental data, we find that the same and the difference ends up being like the same number. And what that means is when you flip a coin, it doesn't matter what happened before. The next toss will be a 50% chance of heads or a 50% chance of tails. So it's the same probability. Again, what happened in the past doesn't affect what happens in the future. So there's this video that we watch on this thing called Gambler's Fallacy, which says like that the past doesn't have anything to do with what's going to happen in the future. Sorry, it's not that video. So I'll pull this up, Gambler's Fallacy.
You've watched that coin flip 9 times. Heads, tails, then heads again, then tails, 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 and what's going to come up next? Tails has been having a pretty good run, so it must be another tails. Or are we due for another heads. There are patterns everywhere in the universe, and our brain is very good at recognising them. Perhaps too good. It can readily see patterns that just aren't there. In truth, there is a 50% chance of heads and a 50% chance of tails after every toss. It doesn't matter what came before, and luck doesn't come into it. At all. But it's hard to shake that feeling that there's a pattern in there somewhere, if only we look hard enough. This is called the gambler's fallacy, our assumption that probability changes depending on past results. And this may explain why casinos make so much money. It's all a matter of probability.
All right, so again, gambler's fallacy, it just states that it doesn't matter what happened in the past. It's not going to affect the future. So when I ask you questions like this right here, if you have 3 tails in a row, should you expect that a heads is more likely? And the answer is no. It doesn't matter what happened before. You still have a 50-50 chance of getting a heads or a tails on the next toss. And same with our last question, if you have 5 heads in a row, should you expect that a tails is more likely? And again, the answer is no. So gambler's fallacy, it just simply states that it doesn't matter what happened before. Each event is independent and will have the same probability of happening in the future. It doesn't matter if you have 50 heads in a row, it's still a 50-50 chance on the next toss of getting a heads or a tails. So your assignment today will be some questions on gambler's fallacy, and also it'll ask you about theoretical and experimental probability. So the link is on Google Classroom. It's a quizzes, and you'll want to finish that for tomorrow.